Science in the Department of Intelligent Systems Engineering and Information Science, School of Informatics, Computing and Engineering, and near and dear to my heart, core faculty of the Cognitive Science program. She's also a founding director of their Cyber Infrastructure for Network Science Center at Indiana University. Finally, she's a fellow of the American Association for the Advancement of Science, was a Humboldt Research Fellow, an ACM Fellow, and she now is the curator of the International Places and Spaces Mapping Science exhibit. You'll see some selections from that in the VIS Arts program, so I encourage you to go and see that work.
Good morning, ladies and gentlemen.
Good morning.
Good morning, ladies and gentlemen.
Good morning.
It's a true pleasure to be here. This is very unique, and thanks so much for having me. This particular presentation is about data visualization literacy. As you might realize, this is an essential skill. I would argue it's as essential as being able to do mathematics, being able to read and write text, being able to do visual literacy. I think today we also need data visualization literacy. The problem I think we all have is that we don't really know how to define it best, how to measure it best, how to improve it best, and how to ultimately determine if we succeeded in improving it. How many of you are teaching information visualization courses? Let's see. All right, so that's good. How many of you have taught more than 10,000 students? So I think you would have to do a MOOC, probably, or you could be very, very old, that could also work. Or you're stuck with a lot of undergrad courses, that would also work probably over your lifetime. So we have to find a way to not only empower each other in this room, but also to empower many, many out there, which want to save lives, which want to build better smart cities, which want to improve all kinds of conditions of human life. And so what I'm going to do here is to present to you a data visualization framework that is meant to empower anyone, and I'm serious about the anyone. It includes my mom, it includes my daughters, it includes anyone, to systematically render data into insights. I think we owe it to the society to find a way to bring rigor to all of this and to bring order to this amazing zoo of data visualizations, as some of you have called it. The second part that I think we owe all the taxpayers that pay my salary, and probably many of your travel costs and other salaries, stipends, is to scale it up. We have to absolutely find ways to bring data visualization making, not just reading, but making data visualizations to a wide variety of audiences. And the good news is that we already have library systems, we have science museums and other places which welcome us to bring new experiences. And of course we have many classroom settings in the formal education. Also, I wanted to point out one opportunity that I see and that just has the most amazing set of visualization challenges in terms of scientific visualization, in terms of data visualization, in terms of algorithm design and mathematics that's involved in that. And so I will introduce you to one of the projects that we are working on. Also, tonight there is the debut of the 15th iteration of the Mapping Science exhibit. And I wasn't sure how many of you had seen maps of science. Can I see another show of hands? How many of you have seen a map of science? A map where the continents are not just Africa and Europe and Americas, but where the continents are mathematics, engineering, biology, many other sciences of our collective efforts trying to understand the world we live in. And so this evening is basically halftime for the exhibit because it's a 30-year effort that we have dedicated ourselves to. And it's a challenge to first of all keep it alive for 30 years, but also to innovate as lots of new things happen in terms of data science, in terms of data becoming available, in terms of new algorithms and visualizations becoming available, and new needs arising in our very fast-paced world. Some of you might already have seen the Atlas trilogy. I know I owe you number 3, that's the Atlas of Forecasts. I'm working on it, but it's taking a little longer than expected because it's complicated. If you want to forecast, you have to embrace computational mathematical models. And as you know, every time you add a formula to a book, you kind of cut your audience in half, right? So I'm still trying to make that work. All right, so what do we mean by data visualization literacy? We believe it's the ability to read, make, and explain data visualizations. And it definitely requires literacy because there's text in the labels, in the titles, in the supplemental text that comes with data visualizations. We need visual literacy, and we also need, of course, mathematics. You need to understand how to place a dot in a scatter plot, for instance. You need to be able to interpret a scatter plot, and so on. And again, just as it is very hard to learn how to read without ever writing something, or to understand mathematics without ever performing it, it's also very, very hard to be good in reading data visualizations if you never get to make one. And so much of our effort has been into developing infrastructures that anyone can use to take a data table and do proper mappings from data variables to visual variables. And one big motivation and kind of sounding board for trying out new approaches is the Mapping Science exhibit. So those of you which haven't seen it yet, it's a 15-year effort to bring these large-scale maps framed, and now in the second decade also interactive data visualizations to many places. So again, there are 100 maps. You could absolutely wallpaper this entire room with them. They are large format. They are great for marking your territory. So if you arrive at a new institution and you're connected with the exhibit, if you're an ambassador, for instance, then you can just hang all the maps. Everybody will notice, and they will ask for a tour or ask for who did this to us and to all of us. The other part now in the second decade is interactive data visualizations. Much more of a challenge. It's not static maps that you can give to a librarian and they will be fine to use in 500 years. No. These are interactive code pieces, and after 2, 3, 4, 5 years, they might not work anymore. Each one of them probably costs $100,000 to develop. There are very few teams on this planet which have the resources to do so. And to create macroscopes that, again, anyone can use. There are many specialized interactive data visualizations, but that's not what we are after. We would like to bring them to museum floors, to libraries, to many other places. And so as you see, this is not my work necessarily. These are 248 map makers from many areas of science, from many geospatial regions. And they collectively created the 100 maps. And then there are 43 heroic macroscope makers, which so far have created 20 macroscopes in the exhibit. Talking about maps, they show collaboration patterns around the globe. And you could overlay your own collaboration pattern. You basically place yourself in the middle, for me, Bloomington, Indiana, and then you would draw arcs to all the many collaborators that are part of my life. You might like to check out funding, who got how much for what. And again, you can go over time, you can animate these maps, of course, over time to see what areas of science are growing because they get more and more funding, which ones are shrinking, which ones are emerging, and which ones are able to attract as many young brains as I see in this room today. It's absolutely fascinating for me to see so many young scholars here. This is wonderful. Areas of science grow because they are able to attract young brains. And these young brains might become faculty members, or they might go out into industry. And actually, that's the absolute question I have. So how many of you are actually planning to go into industry after you graduate, or you are done with your tenure-track job? I'm not going to raise my hand this time. So I saw one hand. That can't be right. Okay, again, how many of you would like to go to industry? 5. That's less than 1, maybe 10. That's impressive. So you're all up for doing 80-hour work weeks. All right. Okay. Then there are maps of science. And again, you can take a map like this and you can overlay your life trajectory. So for instance, my training is in electrical engineering, then I did my PhD in artificial intelligence, and now I collaborate with many, many different scientists across this map of science. You can overlay two institutions, like for instance, engineering at Indiana University and engineering at Purdue University. It's always interesting. You can take patents and you can plot the space of what intellectual property has been claimed. And I don't have time to go into these maps here, but they're all available online. And I hope you go to signmaps.org and check them out. In other cases, mapmakers were interested to understand in how far does Wikipedia cover mathematics, technology, sciences, and what areas are emerging or highly disputed. And again, that can be mapped. Other mapmakers were interested to map the human diseasome and to make that available as an interactive map. So many of the static maps in the exhibit come with interactive online websites. And they're artists, and we very much welcome them. And they might create maps like this one, The History of Science Fiction by Rod Shelley. And those of you which already are science fiction lovers, you might like to find your favorite books in here and then maybe check out the books right next to them. And again, all of these maps can be zoomed into if you go to signmaps.org. Now the second decade, interactive data visualizations. And you have mega regions which redraws the boundaries of the states of the US in new ways based on commuting patterns. And you see that part of the northern piece of Indiana is claimed by Chicago because many in the area and other places are commuting every day into Chicago and back. We have smelly maps. Some of you might be familiar with it. Here you see London, and you get to see which areas are smelling good and bad, and which kind of stress levels are to be expected in what areas of London, and so on. And tonight, you will get to know what maps we have in the 2019 iteration. So please come to the arts exhibit at 6:30. I will be there. Esme, who is somewhere here, she will also be there. And so you can ask the two of us, and we will also demo some of the new microscopes. Oh, there it was. So many of our clients, they are interested to explore today's data and yesterday's data. But what they really want to know is what happens if I fund this team and not the other team? Or what happens if I hire these researchers and not the other ones? Or what happens if I make other strategic decisions? What will happen? What will the future hold? And so in order to answer these kind of questions, you have to embrace computational predictive modeling. And you have to work with economists and physicists and mathematicians and many others which have been developing new agent-based network predictive models. And there are many, many different models which have been applied to the study of science itself. And we now have a number of events that actually brought together these researchers and science of science researchers to understand what we can do together. So there is an entire set of lectures and slide sets available at that website. We had a recent Cellular colloquium on modeling and visualizing science technology developments. All of the presentations are on the YouTube channel. And we also have an entire special issue of PNAS which covers works that have made a difference. And we only included those which made a positive difference, but I think you also actually, in some cases, need negative examples to learn well. We didn't include this, so. I would like to point out this exhibit effort is really a collaborative effort, including many, many others, and many of them are listed here. All right, so this was to just get you interested in engaging in data visualization literacy. And again, we believe that you need to be able to have literacy, visual literacy, but also mathematics skills to be truly literate in data visualization. As you also know, there exist many, many different frameworks and taxonomies to bring order to the probably 500 plus different types of data visualizations. These frameworks were developed to provide guidance when designing data visualizations, but also to facilitate teaching. And they organize data visualizations by all kinds of different facets. Some of them are listed here. And most of them are focusing on reading data visualizations, whereas I will squarely focus on how I can empower and how we can empower many to make data visualizations. The work that you will see here is built on prior work in cartography, psychology, cognitive science, statistics, scientific visualization, data visualization, learning sciences. And many of these areas, all of them, have had their own pioneers which tried to bring order, from Bertin to John Wilkinson to many, many others. Ideally, what we bring to the table for others to use is theoretically grounded, but also practically useful and easy to learn. And of course, that's hard to achieve, but we are trying. It should also be highly modular and flexible, so that it can be adapted as new developments arise. So what you will see is a data visualization literacy framework that was developed using more than 800 plus papers. You will see a typology and a process model together with exercises and assessments, which were all tested in the courses we have been teaching at Indiana University, but also to many students coming from outside through the massively open online courses we have been teaching since 9 years now. The framework was then further refined using feedback gained from constructing and interpreting data visualizations for client projects that the students in these courses engage in. And then we also used extensively learning analytics to understand what works and what doesn't work when teaching to many students. The framework has two parts. One is a typology, just agreeing on standard names for instance, for data visualization types. And the other one is a workflow process. How do you actually go about designing a visualization? Everything has to be simple and as simple as it can be. Ideally, it's just 1, 2, 3. Not more, not 5. 1, 2, 3. We want to have this understandable to anyone. You will also see that there's a correlation, of course, between the typology and the workflow process. So you can overlay these typologies over the process. And so you see that you have stakeholders, which could be yourself, if you're working on your PhD, for instance, or if you have a question that you want to solve. Then you acquire the best possible data, the best data you can purchase, or you have the abilities to scrape from the web, or you have connections to actually get to it. So this is where data scale types come in. Then you will analyze that data in many different ways. You might also run computational predictive models there. Then you would visualize, so it's acquire, analyze, visualize, 1, 2, 3. And then it's picking visualization types or reference systems, as I would call them also. Then adding graphic symbol types, adding graphic variable types to it. Again, 1, 2, 3. And then you deploy. And it makes a huge difference if it's just a large printout, or if it's a massive display wall, or if it's a handheld device. It will impact what you need to do in terms of analysis and visualization. Ultimately, you interpret what you see. And you might realize, oh my God, I missed some data. 1 year is totally not in the data. Or you will see, oh, I only zoom into this geospatial region, so you have to bring in more data. So oftentimes, as you probably all know, you go down this cycle in many times. When I started in this field 22 years ago now, every single step in that workflow was a different code piece, oftentimes written in a different programming language, and of course the output from one analysis algorithm definitely didn't fit into the input, or didn't match the input of the next algorithm. Given that there are typically 12 to 20 steps needed to get from the data to the visualization, it took forever to actually go through that cycle. So all this has changed in the meantime, unfortunately, and there are now plug-and-play infrastructures which allow you to bring in algorithms as they become available in the community. We have been implementing a so-called MakerVis infrastructure where you can upload a CSV file, for instance with publications here shown on the left, And then you can pick different types of visualizations, such as scatter graphs or geomaps or science maps. And then you can use the little panel to do this assignment between data variables, the column in your data table where you could have millions of records, and the graphic variables of your, in this case, temporal bar graph or scatter plot or geomap or what have you. And this kind of infrastructure is used to teach this mapping between data variables and visual variables. Because, as you know, you should only map qualitative to qualitative and quantitative to quantitative, and there are many other things that you should be doing and you need to learn until you really know how to build a proper data visualization. So coming to the typology, you will see insight meets first on the left-hand side. And so these are drawn from prior work. So you start with Bertin, who identified selection and order and quantity and association in his original seminal work in 1967. And you see other works, including also tools such as Many Eyes and Sharpshooter, which also try to bring order to this. And then on the right-hand side, you see the ones which are used in this particular framework. You have different data scales. You have the nominal, ordinal, interval, and ratio scales here. And as you know, you have also different examples here. And some of them are quantitative and some of them are qualitative, and you must understand which ones are which. You might also like to compare this again with prior work. So we use here Stevens' work of 1946, the scales of measurement. But you could also compare it with other proposals that exist in the literature. Again, there's one qualitative in here and 3 quantitative. And as you know, you can do different types of mathematical, logical operations on those types. You have different measures of central tendency, and for those which are still a little bit uncertain which ones are which, there are some examples on the right-hand side. Analysis. I have never encountered a data set that I can just visualize. I don't think that exists out there, maybe in textbooks, but I typically don't work for textbooks, I work for clients. And so in these cases, I always need to analyze the data. And so what you ultimately have is these when, where, what, and with whom questions. If you can get your clients to help you understand what types of questions they have, then automatically, if they have a when question, you can most likely apply temporal data analysis. If they have a where question, then they would go to cartographers, and you would get their geospatial data analysis and visualization methods and tools. If they have a what question, you would go over and make friends with linguists, and you would try to do topical data analysis and relevant visualizations. And if you have a network question, a with whom question, then you can build on and draw from work by physicists and social scientists. And many of you probably in the room also have developed really wonderful layout algorithms for these highly complex networks which our world gives to us. You might wonder how that relates to some other work that has been proposed. And I think there are relationships here. So for instance, geospatial data analysis fits beautifully with the spatial component of data sets that Tamara pointed out. Topical data analysis typically is text, so it's categorical nominal data. You have network analysis, which is, I think, in her framework, relational data. And I think we owe it to, again, the society out there, which needs to have better data visualization literacy, to agree on certain views of the world. And I think there can be multiple views of the world which are relevant for certain types of questions and certain types of contexts. But I think we, as experts in this field, having the unique opportunity to really do this almost full time, we have to provide many practitioners out there, and also those which teach in K-12 settings, or are in need of better data visualization for personal reasons. We have to bring order to this, and I hope we can. Coming over to visualizations, I don't think there is an exact agreement in this room even of what counts as a chart or as a graph or as a map, and many of us still use the terms plot and diagram, and I think it's very confusing for people out there. We have to get order to this, and just like people which were involved in identifying the periodic table of elements had to battle out a lot of personal and professional battles, we have to engage in these discussions to find a language that really works for all of us. And I think it's a compromise for all of us, really. Now, if you have these kind of terms, then you can take tables and you will see, well, there are columns and rows. You can have graphs, well, there's in a scatter plot, you have x, y plots oftentimes, and maybe a third coordinate. In maps, you have latitude and longitude, and in networks, you also have an x, y. And sometimes, well, you have to position these nodes, and sometimes it's just rotation and mirroring invariant. But still, you have this coordinate system. And in some cases, you actually do just two lists of nodes and have linkages in between. So that's a more literal use of a reference system. But if you have these kind of conceptualizations, then you can help people to scaffold. So you can have a scatter graph, and if they understand this, they can also go over to a geospatial map. And yes, it's a reference system, and then they overlay the graphic symbols, just the pure data, just position it in a 2D space here, or in a 3D space if you wish, but be careful there. And then there are graphic variables which are color coded, and you can size coding and shape coding, etc. So the graphic symbols are actually quite interesting. So oftentimes, from what I've seen here so far, you use mostly geometric symbols, and maybe a little bit of text size coding, shape coding, color coding. There are also a lot of pictorial symbols, and I've seen some, but not many. I think it's a lost opportunity in some cases. You have graphic variables, and you can take these two columns in your table and you can create a table from them. And we have done exactly this. So we first design graphic variable types, and we make sure to identify which ones are quantitative and which ones are qualitative. By the way, optics, texture, motion, I have seen very little of it here, so you might like to try them out, especially if you're working on 3D virtual and augmented and mixed reality environments. We also know from psychologists and cognitive scientists which ones are easy and which ones are harder. And again, you can make these humongous tables where you have all your geometric or graphic symbol types and your graphic variable types. And again, those which are with orange triangle are the quantitative ones. And these tables are rather large. And as new possibilities become available via the hardware we're using, you can just extend it downwards. And as new graphic symbol types become available, you just extend it to the right. You see that some of these combinations of graphic variable types and graphic symbol types have not been tried yet, or at least I didn't find them. So it's a little bit like the periodic table of elements, where initially lots of the cells were empty. You also have interaction, and especially in today's time and age, those are very important to get right. So realize again that these two are truly interlinked. You typically start with the acquisition, you then analyze, you then visualize, and then you have that picking of the reference system and designing the data overlays, and then also designing the interaction types. And of course, that all also has feedback going backwards, because depending on what kind of interactivity you want to support, you might have to do something different in terms of picking data or analyzing your data or visualizing your data. And these are just examples on the right-hand side for geospatial, but you could also put a reference system such as scatter plots in there, or science maps and others. So how do you teach this all? Well, we have been bringing data visualization to science museums. So here you see an exhibit that you can actually engage in at the Science Museum in Minneapolis, or at the Coastal Science Museum in Columbus, Ohio. You have a run exhibit, which you can use to run down from a start to an endpoint. Your speed is going to, or your time is going to be measured. You also get invited to enter more information about yourself, including to pick your favorite mascot, to identify your height, your zip code, and also your favorite activity out of cooking, baking, video gaming, sports, etc. You see the correlation there. And then you get to look at your table, you get to identify yourself inside of the data, and you get to compare yourself with your friends, with your family members, and of course also with yourself, because you might have now better ideas of how to do it right, and then compare yourself to others, or to cheetahs, or turtles, or squirrels, which also all have a certain time in seconds here. Then you get to see not only the data, but you get empowered to map the data, either as a geomap here or as a scatter plot. In addition to these museum works, which we very much enjoy and get a lot of fun comments from also, and the team we are working with is very wonderful as well. We have been bringing this material to students from 100+ countries every spring as part of the Information Visualization MOOC. And students which take this course, they get 7 weeks of theory and hands-on practice, and then they work with real-world clients on real-world projects. And so here are some of the client projects, and if you have a data set, a question, and 2 hours of your time, please let me know. We always need a lot of student-client projects because there are a lot of students in this course. And so if you would like to serve as a client, it would be wonderful. And the work that comes out is basically a 6-page paper that students have to write up, but oftentimes there's also an online interactive data visualization. And many students actually then get hired for summer interns, or in some cases got even hired for continuing this work. More recently, we started to develop a course for working professionals. So the IEEE MOOC is designed for learners that have 15 weeks times 8 hours a week. Very, very few people that are in the workforce have so much time. And so this course here is 30 hours total, distributed over 6 weeks, so it's 5 hours a week, which is tough for family life, but I think it's doable. And oftentimes that's basically just work done over the weekend or in the evenings by those which truly want this kind of expertise in their life. And so we work very closely with corporations, like for instance the Boeing company, to integrate case studies that are truly relevant for their engineers. And as part of this, to deal with so many students, we have been embracing learning analytics. And the learning analytics helps students to understand who else is in the course and how are they doing. But it also helps me to understand who needs a little bit more hand-holding or who is too fast for the content we have, because they're going to run out of materials very quickly given their trajectory. And then I can give them additional materials. But also for learning sciences researchers which want to understand how people learn. And of course for the developers of learning management systems, which also have to optimize what kind of bottlenecks exist in the current infrastructures. And again, it answers these when, where, what, and with whom questions. Recently, NSF funded 40+ teams to actually develop infrastructures in support of workforce development. And we got one of those awards, and it's really a very, very fascinating team involving Arizona State University, Northeastern University, and also Oregon State University, and diverse industry clients as well, and government partners. And what we are interested in doing is to develop a suite of data-driven tools to support tens of millions, so this really absolutely must scale, of US workers whose jobs are going to be transformed by AI. We know this. We need to find ways to reskill and upskill them. How do we do this? How do we even find out what skills are obsolete for human users and for human employers and workers? If you look at a map of science, you can actually visualize over time which areas of skills, of human skills, are becoming replaced by AI algorithms. And it's basically like watching a blackout. So you look at the map of the US and you see what kind of jobs are not relevant anymore for human labor. And we have to find ways to, again, make it facilitate a good transition of these current workers into jobs that will be future-proof. at least for the next 5 to 10 years. So using large-scale data sets such as burning glass data and the open course Cellular data, and of course science and technology data, we are working on identifying what are the jobs that are future-proof or emerging, and what are the jobs which are taken over by AI, so that we can guide workers away from those which are taken over, and towards those that are more using the innately human skills that we all have. But then also creating kind of like a GPS system for career management, I would call that, which helps you understand what kind of skills are really relevant for getting your dream job. And you might have seen some of the initial visualizations of LinkedIn data, which visualizes career trajectory using the very rich data that LinkedIn has created. But it's kind of like this, but with a kind of recommender system behind that tells you, well, if you like this course and the other course and you want that job, why don't you also take these other online or offline or residential courses and degrees to get there? And you will have to identify how much time you have, how much money you want to spend, and if you want the scenic route or not. And ideally, we can then also support these kind of requests. So this is a very interesting effort where NSF is really trying to understand how quickly this can be productized, if I can call it this way. So the initial round of funding is 9 months. 9 months, and we are actually needing to pitch to NSF in March, so that actually is only 5 months and total of funding. And after 5 months you get to pitch, and I think it's going to be like in a Shark Tank kind of TV series. And then the next round is 5 million for 2 years. And I don't really know if I actually want that kind of money, and I know this is recorded, but you basically have to create a startup, right? Or you have to have somebody who wants to own it after those 2 years. And it's a lot of work in 2 years. So anyway, there are all kinds of interesting elements of this. And there will be 8 to 10 of these projects going forward. So I congratulate NSF to be so forward-looking, to embrace this challenge that the American workers are facing, and to be rather creative, innovative with the funding mechanisms they selected for this. Okay, so I wanted to leave you with a most fascinating visualization challenge. And it really has something for each one of you if you want that in your life. It's the ambition to map our human healthy bodies. This is not covering disease. This is just the human healthy body, adult body, I think you're all adults here, at the single cell level. And each one of us has about 37 trillion cells. There's a recent Nature paper which has the details, but the vision here is to catalyze the development of an open global framework for comprehensively mapping the human body at cellular resolution. Some of you might have seen the anatomical browsers. Now imagine you could go on a fantastic voyage, some of you might be old enough to have seen that movie, and you could go down the blood vessel system, but you could also go even farther down, kind of like the powers of 10 movies, down to the single cell level. And you could do this to any cell in the human body. And to use this as a reference body of material to understand what makes up a healthy human body as it ages, from 18 to 118 or 180 maybe at some point. So how do you even go about this? And so here in this particular project, it has been set up in a way that there are tissue mapping centers which generate data for 9 different organs and 25 different assay types at the single cell level. There are transformative technology development and rapid technology implementation teams that have also been funded, about 120 people total. They are involved in tissue collection, in creating assays at the, again, spatial transcriptomics, other single-cell technology level. All the data has to be federated, so ontology challenges, data federation challenges. And then there's map generation. That's where our team comes in. And there's another team at the New York Genomics Center, which also is a part of this mapping effort. And there are 2 tools components, and Niels Gehlenburg, who is also here in the audience, is leading one of those tools components. The other one is out of CMU. There will be data storage and also dissemination. The first public data release of HubMap is next summer. Here are some of the organs that we're currently focusing on. As you might know, there are entire NIH efforts that focus on one organ since many, many years. We are taking them all on. We are taking on 25 different assay types. So it's quite a challenge, to say the least. In general, this is the process. You take single-cell omics assays, 25 different types, and by the way, there are multiple ways to get to RNA-seq data right now in HubMap. So this is not even accounted for here, these different protocols which all lead to the same type of data. Then there are multiplex spatial assays, and this data then all comes to the mapping centers, which are engaged in image registration together with CTMCs, tissue mapping centers, feature identification, but then also identifying reference coordinates to arrive at a common coordinate framework. So if you would like to be part of it, and be careful what you wish for, it will consume your life. Please see me. And I saw some presentations yesterday, which I thought were excellent and absolutely relevant here, and I think they got my cards already. So please contact me, or Niels for that matter. It's a really cool team. We even have a dog on board, as you see, and it's a very distributed team. There are quite a number of teams in Europe involved in this. If you are a US citizen and you like network science, this is my plug to apply by Christmas for our neat new NRT on complex networking systems. But unfortunately, this really is only relevant for US citizens. If you like books, there are books here. And if you have any questions, I'm happy to answer them. Thank you very much.
So we're open for questions. I'm told that microphone is now working. If people have questions, please, or comments, please line up. Or if you're near me, I can give you this microphone. That one is good.
Hi, Bob Laramie from Swansea University. I am looking into this literature on visualization literacy, and I also noticed another theme in the VIS literature called sense making. And I wondered how you compare these two kinds of strands. Do you think they're different? Do you think they're the same? What do you think about those two kind of directions?
From what I have seen, and correct me if I'm wrong, sense making is about making sense of data and data visualizations. It's not necessarily going about how do you actually go from the raw data to a data visualization. And again, from the studies we have performed in science museums, and one of the studies actually interviewed 1,000 children and their caregivers across 6 different science museums in the US. And all the study materials are online because we hope it can be reproduced in Europe and Asia also. But from that one study, it became very clear that the average data visualization literacy in the US, at least for people which make it into science museums, is extremely low, much lower than I ever expected. And I think it is that people in this room, we are self-selected to have an easy way to read data visualizations, and we love making data visualizations. And so we are very special in this, and still many people out there, they don't have such ability. So from these studies, and again, they are also written up in a way that we can detail, we found that if people can make data visualizations, if they can layer on more and more and more data onto a reference system, they actually have better ability to make sense, not only of the data and of missing data and of uncertain data, but also make sense of what it means if something is now size and color coded or in a different spot. And I believe if you really want to understand how to improve data visualization literacy, we need to embrace ways to empower, again, anyone to render raw data, ideally data about themselves, because that gives them another hook to engage and to feel that it's relevant for their lives. into meaningful data visualizations. And you could say, well, there's Tableau out there, what else do we need? But I think people also need to understand networks better. I think many of us have friendship networks, have professional networks. We have, inside of us, there are many networks. We are part of many networks, ecological and otherwise. We need other types of reference systems. And I think we also need to agree on a standard way of naming these types of different elements. The 7 types I presented here, there might be others. And we ultimately need a way to empower many to have this kind of training in their lives. And in the US, and maybe that's only in the US, if we could get this into the normal testing schedule, then teachers would teach to the test. That's what's happening in the US. So one main ambition, and a big ambition, and maybe it's impossible, is to find a way that we can have not only rigorous tests for mathematical skills and literacy skills, so reading and writing, but also very rigorous tests in the K-12 environment for data visualization literacy. I believe this is absolutely needed in today's time and age that society and anyone has this kind of ability. And maybe the kids which are currently in the school system will then teach their parents how to do it right. And maybe some of those parents are congressmen and others, and that would also be useful.
Thank you.
Thank you, Katy, for your exceptional work over 20 years and for promoting and distributing, disseminating the work of this community and others in a worldwide way with your ambitious series of exhibits and your magnificent books that are just wonderful coffee table and inspirational works. So all very, and for educating so many. Your talk gave that story very well. But I was aware as I was listening to it that your focus here is at least on large-scale visualizations on the maps, on the walls, on large screen displays, on animated surfaces or walls. And I wonder what your reflection is, or what directions or what promise you see for the idea of visualizations on these devices. They become high resolution, very powerful devices, and those are the currency in a worldwide way. And if we're to make visualization widely influential, I'd say we need to address the goal of serving people's needs for medical information, for legal information, financial information, personal and family relationships on the devices that are used by billions of people. What do you think?
So we have a number of projects, which I didn't get to present here, where we do mobile-first visualizations. And then they also work on the desktop, but they are designed for being on phones. One of these projects is, for instance, environment for epilepsy patients, which have the desperate need to not only have access to their health records, but they also need a way to write down what happens to them after they take a certain medicine, or when they have what kind of seizure and how they felt. And ideally also communicate this to their doctors, but also to their family members. So here, having something that's always with you, not a big computer, but your phone, where you can very easily type things in, is very, very important. We started to discuss collaboration opportunities with Live Omics. Some of you might have downloaded the health trackers that Live Omics now provides. These kind of trackers, which kind of nudge you to do the right thing, to take the extra steps until you get to 10,000, to eat the right food, and to also stay otherwise healthy and sane in this very fast-paced world, I think are very, very much needed, and ultimately can be connected to your true health records that are available to each one of us if we want that. And going forward, I think many patients will opt in to actually connect all of their data sets this way with the doctors, and they themselves have a better handle at dealing with these kind of situations in their lives when really one disease really takes over their life. In other areas, like for instance in HubLab, we have developed virtual reality interfaces where you can actually do some of the registration of tissue pieces by just having two handheld devices. So you have a virtual kidney and a virtual tissue piece that you got just dissected, and then that gets inserted. So here we are using virtual reality technology. But coming back to your question about how do you deal with these small devices, even though some of them have very high resolution, so the number of pixels in some cases is comparable to what you have on a normal screen. So if I put on my glasses, then it's almost comparable. And if you have better eyes than me, then you don't need your glasses. So how do we make it then that we have coupled windows on those? I think we need new interface methods for the interactivity. But I think you still want to potentially have two visualizations where you can pick a data point in one and you see it in the other one. I think the smaller your device, the harder this will get. Also, my fingers seem to be too big to then pick certain menu items. So I think there's lots of work to be done, and I hope to learn from those which are really focusing on this. I think my focus, as you pointed out, is on large-scale visualization, and in many cases we print. And we have been surprised by the take-up of just large-scale printouts of all kinds of data, because people are very comfortable with paper. Paper has been in their lives, not literally, but it has been in our mankind's life for thousands of years. And so just unrolling a piece of paper, starting to annotate it with a group of interdisciplinary scholars is very powerful. And having something physical, be it a printed 3D object or be it a piece of paper which has been printed on, is very useful for many types of prototyping.
Still, I would like to encourage you to include that design form factor in your slides, in your presentations, in your exhibits, and your books, and also for this audience. I think for this community, our next challenge is to make visualization widespread. We've succeeded with the narrow communities of our colleagues and researchers and engineers, etc. Our next major challenge, I believe, is for us to address the needs of a wide range of people and serve their needs through the devices that are in their pockets and are in daily use. That's the big challenge. Thank you.
And I think it's really both. It's embracing the new hardware as it becomes available, but it's also embracing ways to make it easy for people to understand that data mapping to the visual and graphic variable mapping. Because if you're stuck on your handheld device with 3 bars, not 4, or 2 pie slices, not more, you know what you have in the lower level of USA Today. If you're stuck with that, it's not going to go.
I think that's really unfair. There's enormous power for great visualization, of rich information, but the techniques for interaction that allow you to drill down and examine and move through the large data spaces is really our challenge. And we can do that. I mean, we've done it on the megapixel and the 100 megapixel displays. Here we have a megapixel. The form factor is smaller, but it's the universal one. We need to go there.
Yeah. And I think you misunderstood. I didn't argue that it can't be done on the smartphones. And I think what Google has given us is beautiful because it has trained almost everyone to read maps. That was not the case before Google Maps came along. But what I was arguing for is that we should have something like Google Maps, but for networks. We should have something like Google Maps, but for tree maps and for Sankey diagrams and for cartograms, which most people out there cannot read. Please.
I want to change topic a little bit now. About like, I feel find this word fascinating that what about AI is fine. So it is. Okay, first I want to change topic a little bit. So I really find this work that we proposed on helping AI displaced workers find different kinds of professions very fascinating. Are you like, is this more for government to recognize what they need, or is it more for the workers to actually educate themselves differently? Because having read a lot about people that resist change, and there's plenty of them in the United States, right? It requires persuasion, right? To really change their lives and really take on the task and educate themselves. How do you like persuade them to actually make that step and do this and in what direction? And how do you gauge the skills that they may have and then develop them further and add to them and use the best skills that they have? That's a very complex, high-dimensional sort of data problem, right? And then also create the visualization on the mobile phone that you can build up to events, spells thesis, right? So how do you...
So NSF actually has set up 2 tracks, A and B. We are part of the B track. The A track looks at how employers can benefit from data sets that now exist and can be combined and federated, and algorithms, including lots of machine learning algorithms that can now be used to create recommender systems, for instance, and visualize on a large scale what patterns, trends, and outliers exist in that data. But then in track B, we are helping the American worker. So we are focusing on people that, for instance, go and benefit from the partnership between ASU and Starbucks, where now Starbucks employees can take for free or at very little fee courses at ASU which are good for them. So it's a societal benefit that is behind this collaboration between Starbucks and ASU to just offer this. And to be honest, many of these Starbucks employees, after taking these courses, they go on to much better paid positions. So Starbucks is supporting them to take the courses and then they leave them. Some employers might not like that, but Starbucks is doing that. So there are many examples like this where there are easy ways in because these are the normal ways that people already take. But then it's important for many to first of all realize that certain jobs are obsolete for human workers. So if you have a daughter which is currently trained in, let's say, maybe I shouldn't go there. Anyway, there are many jobs which people should not study right now. They will be taken over by algorithms. And then there are jobs where power dynamics will change drastically. Like many of you probably arrived here by plane. And you might realize that planes are not driven by pilots, but they're driven by algorithms. And it feels very different to a pilot if you're driving an Airbus or a Boeing machine. And if you ever get to talk with a pilot about this, it's fascinating. So it feels very different to be pilots, depending on what kind of technology they are using. So I think we all have to understand that in order to be productive and happy also in the future, we have to learn to live, learn, and be with these artificial intelligences, and be it robotics, be it IoT, sentient architectures, be it wearables, which many of you already have on your wrist. Many of you have Fitbits, and many of you might be part of Strava, and that's all good. But we have to learn to live this way, and I don't know if this answers your question, but I think there are many, many ways that you can empower people to understand, okay, these are the jobs which are kind of future-proof still. These are the different courses and credentials that can get you into these jobs. And there are different routes to go there. And I think for me, so far the most fascinating out of this project is that whenever you take a course, and that could be a workshop at this conference, it opens certain doors, but it also keeps others closed. And I think many people have the jobs they have today because one of their family members had it, or their grandma, or their uncle, or their parents thought, oh, this is a good job for you. And then they just went for it. They might not see that this course they took at this conference here actually opened 100 doors for them. They might only see that one job that somehow they think is their dream job. And I think by helping people understand how skills are aligned to the jobs that exist today and in the future, that would be very valuable.
So how would your teacher displace a coal mine? Displaced coal miner. Like, that kind of person.
Yeah, and I come from Leipzig, right? We had a lot of talkabouts everywhere around there. I think it will differ for different people. Some are introverted, some are extroverted, some have one learning style, some have another learning style. I think it has to be precision education ultimately. Just like we now have precision health and precision medicine, I think we need to get somewhere where it's really specific to the abilities and interests of a human person in question. They should be getting different choices that they can take in their life to go from one lily pad, if you wish, to the next, and ideally they never jump on lily pads that is just about to become obsolete.
I think it would help to have some advice on advertisers and marketing.
Yeah,
Probably
yeah.
contribute a lot.
Or,
Thanks a lot.
yeah.
Okay, just a quick question. Stephen Redmond from National College of Ireland and Accenture. Two things. One thing you said was for data literacy or data visualization literacy, you need to be literate. Okay? And also actually maybe going to Ben's point about the mobile devices. What place for voice in this?
I like this. And it's not just voice, it's also gestures and body movement and facial recognition. We have not explored that space much. Right now, it's really focusing squarely on typed text and reading text, mathematical literacy, and visual literacy. And those three are actually well defined by OECD, for instance. There are many standard tests for those three. I don't know if there is an official test for gestures and facial recognition and bodily movement, and that would be administered in schools, for instance, to understand if people can express themselves intelligently, right? I don't think we're there yet, but I would be very interested to get pointers to that. I think it's very important to look at those other ways of interacting with robots, or sentient architectures, or wearables as well. I think it's really a future where we have to embrace these IoT or IIoT data streams. And I have seen some of it in the posters and in the short presentations yesterday, but I think we need much more of this. We need to analyze that rich real-time data we now have, interacting with each other, interacting with computers, and computers interacting with computers, or robots or puzzles.
Thanks, good.
Well, we've reached the end of our time. I want to thank our speakers for